Today's webinar is on the topic of saving 2x visitors with practical equivalence. It's a very interesting and an idea that we found in research. It has been implemented at a few places. I'll be talking about it all and I'll try my best to share what I've learned about practical equivalence with all of you. So without wasting time, let us get started. Some sanity things, if anyone wants to drop a question, they can drop in Q&A and I'll be constantly checking it throughout the presentation. Finally, I have a quiz for you guys and I request you all to join the quiz through the link in the Q&A. And on the fourth slide, I'll also be showing you the QR code that you can scan with your phone and join the quiz. So wonderful. So I'll start with sharing this idea. I think you all must be able to see my screen. If there is a problem, just let me know. So today's topic is save 2x visitors with practical equivalence. A quick introduction about me. So I've been doing product and research at VWO for the past 4 years. I have built the new stats engine at VWO. In the process, I've also been involved in writing a lot of things about experimentation. I've also been writing a blog called VWO Stats Blog. I've also been speaking at conferences and opportunities to teach about experimentation. And I've also been internally teaching a lot of sales and marketing people the nuanced concepts of statistics of experimentation. I've been talking to a lot of customers in these past 3-4 years, a lot of VWO customers and solving their problems associated to A/B testing. So that is the source of my understanding of a lot of these pressing customer issues. And finally, I've been involved in reading and learning about experimentation. So recently, I've moved out of VWO and now I'm committed to sharing all my learnings with the broader community. So with that, let's move ahead. I'll give an overview of the webinar today. So today's webinar is on this idea of shifting the null hypothesis. It's an underexplored idea, not a very popular idea, but I found that it has a lot of benefits in the current landscape of experimentation, as it can help you save visitors. I'll show that to you in this webinar. I'll explain why we should do that, and hopefully you'll learn a bit about minimum detectable effects and a new concept of region of practical equivalence. One thing that I want to get cleared out of the way. So I'll come to that. So we'll start with understanding shifting the null hypothesis, and then we'll transport this idea into the Bayesian domain because it's easier to understand there. And there we are calling it region of practical equivalence. So I'll explain this transfer as well, and I'll explain the region of practical equivalence. And finally, we'll discuss 2 modes of testing with which you can save these visitors, save a lot of visitors. So that is the rough structure of the webinar. Now, I want to highlight one thing. So firstly, this is the QR code for the Mentimeter presentation. And I urge you all to sign into this QR code. Just you can scan this and you can become part of the quiz that I have. Or you can also go to the link in the chat that I've pasted in Q&A and you can see there as well. So let me just check if there is any question in Q&A. No. Okay, great. So yes. So one thing that I wanted to get cleared out of the way. So this concept of region of practical equivalence is something that we built at VWO, and that is why a lot of these later concepts that I'm discussing in this webinar might be very much related to the new stats engine of VWO. But I want to clarify, I'm not trying to sell anything to you guys. This concept exists outside VWO as well, and it is not very hard to shift the null hypothesis in your calculations as well. My only, I'm not getting any sponsorship for this webinar or any vested interest in promoting the concept of rope from VWO. But my only motivations behind sharing this with all of you is that I am very passionate about the research we have been doing, and I feel I want to share that with as many experimenters as possible. Further, for people who do use VW, it is just an added advantage that they'll be able to use this technique already implemented in the new reports. So that is like it. With that, I would want to move ahead. And yes, I hope you all have signed into this puzzle. I request you all so that this webinar is made more fun by your participation. So now coming to this idea of shifting the null hypothesis. If there is any problem at any time in my voice or in my video or anything, just let me know in Q&A so that yeah, I'm informed. Thank you. Thanks a lot. So shifting the null hypothesis, understanding the concept. So I'll first take you through this story on why we should even shift the null hypothesis. So this is a chart that I took from a blog that was written by Georgi Georgiev from Analytics Toolkit. And this chart plots the distribution of uplifts in data, essentially. So like, what is the observed effect uplifts that you see across multiple tests? So if you see here, and this is relative uplifts naturally, the idea is that a very large percentage of uplifts are centered around zero. So a large sort of set of uplifts do not have any true impact. So most number of experiments that you run, and this is something common that you'll find across many studies that has been done in bigger firms and bigger companies that have been running experimentation for a while, that most tests give a zero uplift. And for some few, like there are few gems that give you a significant or large uplift, but they are rare in number. So always you have lesser number of uplifts and more number of so you have lesser number of true winners and more number of false bogus ideas in testing. So this basically highlights a fundamental asymmetry in test uplifts that when you go out, you tend to find more of just normal non-impacting ideas and less of those gem insights that actually move your experimentation journey forward. Now, this webinar is about how we can utilize this asymmetry in in your A/B testing, in your A/B testing framework, essentially. To explain you the concept on why we want to use this asymmetry and why there are two sides of this asymmetry, I am wanting to start with a thought experiment for all of you. And for this thought experiment, I would want you guys to be logged into that Mentimeter because I have a question there as well for this thought experiment. Now, the thought experiment is that you're looking through the old photos that your family has collected, like old photographs. And just imagine that you have a big box of photographs and you have a lot of like printed photographs on that in that big box. Now, the first question is that you are looking for photos of old granny, probably an old family member, and you're wanting to find the photos of that old family member. How do you search the photos of old granny fast? So that's the question. I'll present my screen. This is the first question that I have for all of you. What happened? Yes. So I've presented. So this is the first question. I request you all to take a jab at this question. There are three options. The first is that you are looking at all photos roughly with the same amount of time spent. Like, so you're picking a photo, observing it, then keeping it aside. You're picking a photo, then keeping it aside. The other is that you are carefully looking before discarding the photo, but you are quickly keeping whatever looks like granny. So whenever you see something that's looking like granny, you throw it in the keeping pile and you're discarding uh, carefully. The last option is you are discarding quickly and you look carefully when a photo looks like granny's. So take a guess. Take a guess what would be the best approach. And this is the crux of the webinar. This is the crux of the idea. So I urge you all, I request you all to take a minute and participate. And naturally, I have the Mentimeter for those who have not been able to sign into the QR code. I have the Mentimeter in Q&A as well. No one? Okay. Anyone else wants to take a guess, or the question is too? Okay, I'll move forward. The correct answer is good. Like when you're looking for photos of old granny, you are discarding quickly whatever does not look like having people or having granny in it. You discard quickly, and you look carefully when a photo looks like granny. So you observe it, and when it does, you keep it in the granny pile. So, oh, sorry for the Grammy fast, but yeah. Moving ahead, the second question, and to draw the contrast between these two things, you want to discard any photo with a light burn. So now the second task is you are filtering out photos, and you want to discard any photos that even have a slight burn, so that all bad quality photos are discarded and left aside. What is the best strategy in this scenario? Again, we have the same three options. Inspect each photo with roughly the same time. Look carefully before discarding. Quickly keep what looks like a burnt photo. I'm sorry for some of these errors because I made these puzzles like very today only itself. So I had short time. Thank you for understanding. But the idea is look carefully before discarding and quickly keep what looks like a burnt photo. And the other is you discard quickly, but you look carefully when a photo looks like burned. Anyone wants to? Okay, I think the wrong wording is confusing. I understand. Now the thing is, the idea that I want to tell here and I want to highlight here is that in the first case, when you are looking for the photos of old granny, when you are wanting to select something, you want to discard fast and you want to observe carefully. But when you are discarding anything that is bad and you have basically a higher tolerance for whatever is good, then you want to filter out fast. You want to basically uh, you want to keep whatever is looking good, but whenever something looks burnt slightly, then you spend more time in discarding it. And this is the central idea behind the shifting the null hypothesis and how you can utilize the asymmetry that is there in uplifts. So moving ahead, I want to first explain that what really is MD so that you can differentiate equivalence from MD very clearly. So to understand what MD is, you can think of this analogy that you on a distant wall somewhere, you have a straight line which shows you sort of uplifts and then a center line for zero on that wall. Now the idea is that when you're looking at the wall from a distance and you're not wearing glasses, so your vision is blurred. So the idea is that the higher the power that you have, the higher the power for the lens that you have, the more clearly you'll be able to see improvement is equal to zero. And the lower the power that you have for your glasses, the less clearly you'll be able to see when an improvement is zero, essentially. So this is precisely the thing with MDEs as well, that the minimum detectable effect is directly derived out of the power that you are allocating to the test, which is sort of like how many visitors you are giving to the test. So if you are giving more visitors to the test, then you get a sharper vision, you have a high power, and you are able to detect differences very close to zero also. Like if something is even 1%, I'll be able to detect it as improvement is equal to 1%. But when I have low power, I have low sample sizes, then I cannot detect something of 1% or 2% range because it's blurred out for me. So that is the intuition that I use behind MD. And yeah, so this is something that we'll use when we are shifting the null hypothesis. So now moving ahead, and let me see if I have any questions. Yes, I have a question for you guys. Uh, Anyone wants to define MD here? No one? Okay. I'll probably, okay, MD is the minimum effect you can detect in a given sample size. So I'll move forward with the story. I think very less engagement on the Mentimeter today, but it's okay. So now moving forward with the story that how MD and sample sizes are related, and I've drawn a diagram for that essentially. So this gray distribution is the distribution of your true uplifts, what your true uplifts look like. And MD is what of an uplift that you'll be able to detect. What is the smallest amount of uplift that you'll be able to detect? So when you have a larger minimum detectable effect, like when you have low sample sizes, then the MD is larger. So you are not able to detect smaller effects. And when you increase your sample size, you sort of bring in the boundary of worse and better closer. So in the picture below, you are able to sharpen your vision and you are able to detect differences even larger than 3% and lesser than -3%. So that is how MDs work. So if you give more sample sizes to your study, you reduce, so you reduce the MD, you are able to detect smaller and more nuanced differences, but they are symmetric around zero. They are symmetric. So something to be detected as worse will need to be worse than -3%, and something to be better, it'll need to be better than 3%. And now the interesting thing with A/B tests is that if there is no impact in your test, which as we saw in the first slide is the most dominant scenario. So when you have no impact, then you need to run the test the whole course. There is no way to stop it short. So in sequential testing, you can stop the test early if you find the difference to be statistically significant on either side. Either it is worse or it is better, you can stop the test early. But if there is no impact, then you need to run it the whole course. Then you need to run the test for the entire sample size that you have pre-decided for that test. So this is very uh, what do you say, non-helpful in A/B testing, because most of the times you have no uplift, and most of the times you need to then run the test its whole course, and that ends up costing a lot of visitors. So what happens when we shift the null hypothesis? So shifting the null hypothesis is the idea with which we can save some visitors. So essentially what happens is MD will always be symmetric uh, given a number of sample size that you are running the test for. But what you can do is that you can shift the null hypothesis itself. So shifting the null hypothesis, I'll give a bit about what the null hypothesis is. So when you are calculating statistical significance, you essentially first define the null hypothesis that control and variation are the same and improvement is equal to 0. That is our hypothesis, and we try to calculate the chance of observing the data, whatever data that you have gotten in the test, chance of observing as extreme as the data that you have observed, given that the null hypothesis is true. So if the improvement is 0, what is the chance that you see an uplift of say 5% or 6%? So that is what frequentists would calculate generally. And what you can do is you can convert this improvement is equal to 0 to improvement is less than 2% essentially. So you can shift it from 0 to essentially 2%, and then you can calculate the p-value accordingly to the new null hypothesis. And this is not a new technique. I think if you search ChatGPT or any method, you'll be able to find the formula hack for shifting the null hypothesis, essentially. And if anyone has problems in that, I'll definitely be helpful in sharing the formula. Now, what happens and what it does when you shift the null hypothesis? So in this case, the MD is 5% from 0%. So better is after 5% and worse is below -5%. When we shift the MD to 2%, what interestingly happens is that now also MD is like, given the same sample size, your MD is 5% around the 2% null hypothesis. So you are able to detect winners when they are greater than 7%, but you are able to detect losers when they are less than -3%. So you have sort of given an asymmetric bump to not better, and sort of traded off uh, slowly detecting what is actually better. So this is something that you were doing with searching for photos of old granny, that you wanted to discard fast and you wanted to sort of select carefully. So this is exactly that. And what it helps you do is that when you run this in a sequential testing framework, then a lot of visitors, and because the relationship is exponential, then you are able to save a lot of visitors because it calls out early into the test that something is not better in the running test. So when something is not better, you can stop it with confidence that naturally you know that something not better might be still be between the range of 0 to 2%. But if you are okay letting the range of 0 to 2% go to be disabled, then you can happily discard a lot of ideas quickly and earlier into the test. Any questions up till now? Oh, okay. Yeah. I've shared the link of the quiz, Vincenzo, again. Yes, thank you. I've skipped some questions. Okay, yeah. Now, I want to show you in practice. Shifting H naught means to move the MD from no. So okay, one confusion that has come up. Vincenzo asks that shifting the null hypothesis means that you are setting the MD to 2%. No, shifting the null hypothesis is essentially you are shifting what you consider as equivalent. So earlier you considered improvement is equal to 0% as equivalent. Now you are considering anything below 2% to be equivalent. So shifting the null hypothesis is something that you do in the formula when calculating the p-value. I'm not going into the details of statistics. You can find this method definitely implemented in VWO because we implemented it there. I'll be discussing later on how you can shift the null hypothesis in VWO. For some other tools, you can run one mode, non-inferiority mode of testing. I'll show how you can do that. But it is not changing the MD. So MD is always above rho. So above whatever is the baseline for your null hypothesis being shifted. Like here, as we see, MD is symmetric from 0%. Here, MD is symmetric from 2%. So that is like it. I hope I was able to explain, Vincenzo, or else I'll explain later. So yeah. Now I'll show you. I ran some very interesting simulations, and I have over 2,500 synthetic A/B tests that I ran. And what I did for those A/B tests was so yeah, not 2,500, sorry, 25,000 A/B tests essentially. So what I did was I had 500 A/B tests for each uplift, and I varied uplift from minus 25% to 25%. And then I ran them in a sequential testing framework, and I tried to see that when is 80% power reached for what samples for both the decisions of disable and winning. So I want to show you this. Over time, rope is changing. So here, rope is 0. Like when you go to the start of the test, the rope is the shift. I'm sorry, the shift and null hypothesis is 0. So when the shift in null hypothesis is 0, then you see that disable and winning recommendations almost take the same time, same sample size for different uplifts. As the shift in null hypothesis, so as you go on shifting the null hypothesis to the right, what you see is that the disable becomes very cheap. Like it requires lesser visitors, and the winning recommendation is requiring more visitors. So for a 10% uplift, if you see, then winning recommendation is almost requiring, when there is an actual 10% uplift, the winning recommendation is requiring almost 5,000 visitors, 4,800 visitors. And when there is a minus 10% degradation, then the disable recommendation is being called out in 1,500 visitors only. So this is the benefit of fast discarding early. Any questions on the simulation? No. Okay. So this is the benefit. I want to ask the question. Okay. No. I'll move ahead first. Just a second. Do I have questions? Yes. Now the question, the idea, the interesting idea is that because winning ideas are much lesser in number and losing ideas or no impact ideas are much higher in number, when you look over tens and twenties of experiments that you have run on your platform, you are able to save a lot of visitors in A/B testing, because you save for all the times when you were able to disable faster, and you spend extra visitors only on those few times when they were actual winners. So if you think from the photo searching analogy, you'll be able to understand how we are able to move fast. So yeah. Now I'll move towards an interesting idea. And this idea is the region of practical equivalence. So shifting the null hypothesis is the technical frequentist version. And I started with this so that this bridge between frequentist and Bayesian is understood well. Region of practical equivalence is the Bayesian interpretation of the same idea. And it actually summarizes and makes the idea much more simple and succinct. So that is why I'm sharing this here. So firstly, I want to share a bit about Bayesian and frequentist. So what I've been sharing in previous webinars as well, that with an uninformative prior, Bayesians work the same as frequentists. So I'm not going into the detail of this argument. What I'm just trying to tell you is that and I'll share with anyone who wants to see my Bayesian versus frequentist webinar. But the idea is that in frequentists, if you see, we deal with t distribution. So we assume the null hypothesis. We assume that the improvement is 0. And then we have this t distribution that tells us that what would be the distribution of observed data if the actual uplift was 0. And from there, we calculate the p-value. In the Bayesian system, we do something different. We have on the x-axis, we have the true uplifts, that what are the possible true uplifts that there might be in the test, like what is the actual impact. And then we have the observed mean of the impact. So basically, if you have observed an impact of 5%, then this distribution tells you that what is the chance that the true uplift might be 3% or 5% or 7% and so on. So Bayesian and frequentist are interpretationally different, but when the priors are uninformative, they perform the same. So essentially, it is only about shifting your view from the frequentist view to the Bayesian view. The Bayesian view will allow you to add priors, which will make it more accurate. But even if you don't have the priors, you have the same results from frequentist and Bayesian. So now what I want to tell you and what I want to show you is that with Bayesian, you are able to understand this idea of shifting the null hypothesis much more easily and much more intuitively. I prefer the Bayesian explanation because it's usable, it's more usable. It does not matter like if you even calculate it via shifting the null hypothesis or the method or using the Bayesian thing, you'll get the same answer. So you have the freedom to interpret it in whatever way you like without any loss in accuracy. So now, when we translate this system into the Bayesian system, what we get is very interesting. So this is our curve of possible improvements in our Bayesian system. So, and this hump in the curve shows where the likely improvement is. This curve can be anywhere on the number line. It is usually centered around the mean of the actual observed uplift that you are seeing in the test. Now, what we do with by shifting the null hypothesis is that we very cleanly get 3 regions. So we shift the null hypothesis up till a point which we consider equivalent from a business standpoint. Now, if we divide this into 3 regions, we have a small region in between, which is our region of practical equivalence. And then we have the region for better and we have the region for worse. So essentially, if I'm saying my minus 2% to 2% are uplifts that I'll consider equivalent, then the area between minus 2% to 2% becomes my probability of practical equivalence. And the area greater than this becomes my probability of better. So anything above 2% is better and anything below minus 2% is worse. So this is equivalent to shifting the null hypothesis in the frequentist domain. This is slightly complex. So any questions up till now about this Bayesian interpretation? Because I'm moving forward with this Bayesian interpretation uh, for explaining the two modes of testing. No, great. So I'll move forward, and now we are coming up with the interesting idea here. Now, what I want to first tell you is that this practical equivalence, you can essentially set in. So I implemented the system at VWO. We implemented the system at VWO. There we have given you something called rope, which is the region of practical equivalence, and we allow you to set it for different metrics, and you can just save it with the test. The larger the rope, the faster the disabling, and the slower the winners that you get. So this is a configurable quantity that you can set. By default, we had set it to -1 to 1%. Now moving to the two modes of testing and how we have derived these two modes of testing. So now the question, when you divide this whole curve into three regions, is that you are sure that you want to deploy the test when it is better. You are sure that you want to disable the test when it is worse, but you are not sure what to do with the region of equivalence. Turns out you can do two things with the region of equivalence. The first is that you use this probability of equivalence for disabling. So if I merge this with worse, what I get is the probability of not better. So my null hypothesis becomes that uplift is less than X%. X% might be 1%, 2%, 3%, whatever value you set. So the null hypothesis is that uplift is less than X%. The alternate hypothesis is that uplift is greater than X%. And this approach allows you to disable fast and deploy slowly. So you are able to more accurately get into the winners, and winners will take more time, but disabling will be more easy. Exactly like the scenario of old granny photos that I shared with you. So this is what I call the superiority mode. So where you are testing for something to be better. Now we come up. Before we go on to the other mode, which is non-inferiority mode, I want to share that what this mode of superiority can help you do. So the mode of superiority can first help you run more tests, because you know that bad ideas are disabled early, so that naturally gives you a boost at being able to run more tests more faster. You don't need to go towards the end of the test for any non-performing idea. So firstly, it allows you to run more tests. Secondly, it allows you to create variants of your idea. So when you're moving with a discard fast approach, what you can do is, suppose you have gotten a hypothesis and you're running an A/B test for that hypothesis. So what you can quickly do is that you can discard the discard bad ideas quickly. So you can create some variations of your idea. So suppose my idea was that uh, I'll probably show social proofing on my website. Now what I can do is I can try out 3-4 different ways of social proofing, and whatever is not working well, I can that will get discarded slowly, fast, early into the test. So this gives you the freedom to create 3-4 variants of each idea that you're going to test. Now, finally, another last benefit of the superiority mode is that when you do get winners, then they require more visitors, but they are also more accurate. So because if you look here, by shifting the null hypothesis, you are not considering anything below 5%, like 7% to be a winner. So when you do get a winner, they'll be more strongly confirmed. So that is the benefit of superiority mode of testing. Finally, moving to the other mode of testing that you can utilize. That is the non-inferiority mode of testing. This is when you use equivalence to actually deploy. So what you say is that I'll use the probability of equivalence to deploy. So I'll sum these up, and whenever this crosses 95%, I'll deploy, and I'll deploy early. So the idea here is that you are able to deploy any variation when it is not worse than baseline. And you only disable a variation when it is actually worse. So the null hypothesis here is that the uplift is less than minus X%, and it is harder to discard. And the alternative hypothesis is that uplift is at least better than minus X%. So if I'm tolerant up to minus 2% of a drop, then basically I can detect a winner much faster, and I can run a test much. I can deploy a winner much faster and have lesser visitor counts in the test. So non-inferiority mode is exactly the opposite. Now I want to show you the graph for non-inferiority as well. So again, I ran the same simulation that I had shown you earlier. Earlier, I had shown for the superiority mode where disable becomes cheap and winning becomes costly. In the case of non-inferiority, it is exactly the reverse. Winning becomes cheaper, winning is faster, and disable becomes harder. So this is exactly like the case when you are trying to remove photos that are light burned from your photo collection. So this is the case of non-inferiority. Any questions up till now on that? Okay, great. I hope I'm able to explain. So as the rope value becomes bigger, you are able to deploy faster. You are able to declare winners with much less visitors. Now, why would you want to run non-inferiority tests? Firstly, and this is a very beautiful idea. After a while, when you have developed your website, and especially when for a long period you are not experimenting when developing your website, a lot of clutter gets collected on the website that is not helping your conversion rates. It is always a good idea to remove what is not helping on your website and make your website cleaner. So first, a reason to run non-inferiority tests, which are another way to say not worse tests, like is you try out to create a variation by removing one part of your website, or removing one widget, or removing any one, maybe anything it can be, but by removing elements from your website. And in that, if you run non-inferiority tests, you are like, you remove 5 things and you create 5 variations, and you are like, whenever the conversion rate is not worse, then you accept the variation. But when it is actually becoming worse, so if you remove something and it actually becomes worse, you want to be doubly sure. You want to be doubly sure that removing this is actually hurting conversion rates, so I do not remove this element. So reduction tests are a very good idea to clean up your website. You can run reduction tests, and non-inferiority mode is a very good mode for running reduction tests, because whenever something does not impact your conversion rate by more than a margin, you will sort of you will let it pass fast. And only when something is actually impacting, that is when you'll spend more visitors on it, and then you'll retain that element for your website, essentially. So this is again like the light burn photos experiment. The second reason to run guardrail type checks is that run non-inferiority tests is that you set guardrail type side checks. Like for instance, you have a primary metric. You can set that, okay, these 3 metrics in my test should not be going down in the process of testing. So you can set it up as an extra check that will sort of like, while guardrails are required to disable early and to stop harmful experiments from impacting your crucial metrics, these can be some lower version of guardrails that you just want to confirm that they are not impacted negatively at the end of the test. So you can just run it sort of like in the not worse mode. So like if I'm making a new design change, then I just want to confirm that my conversion rates are not negatively impacted. So I run a non-inferiority type test. Finally, if you have a very low visitors or low traffic on a page, you can start by testing in the non-inferiority mode because it's cheaper. It requires low visitors. You'll be defending for your conversion rates to not go down, and slowly as you grow, you can run tests with superiority. Great. I've skipped the questions, guys, in this webinar because there was not a lot of engagement to that. That's why I think we are coming to a close early as well. So now we are on the last slide. And here I just want to give some practical tips about setting practical equivalence in your webinar. Any questions up till now before we move ahead? Okay, wonderful. So setting practical equivalence, significant visitors can be saved even with small shifts. So even shifting the null hypothesis by a small margin will help you save a significant bunch of visitors. Why? Because sample size and the null hypo and MD essentially is has a inverse exponential relationship. So you'll be able to disable much faster even with a small shift. So do not undervalue. Even if you can set 1 or 2% for this practical equivalence region, you are good to go. Secondly, decide equivalence from a business standpoint. So you should ask yourself, what is that equivalence level below which I do not have a business value for an uplift? So generally, when I say 1% or 2%, I mean to say 1% or 2% of the baseline average. And you should decide, like, if my baseline average is 10%, then 2% of 10% is 0.2%. And I should define a range that I do not care about uplifts below 10.2%, like variance below 10.2%, something of that sort. If you are early disabling or early deploying, you should ensure sequential correction. This method does not work with fixed horizon testing, like which is not sequential testing, because you are using up the entire sample anyways in fixed horizon testing. So this works only in a sequential testing framework, and ensure that you are properly corrected for the sequential testing framework before disabling. Finally, do not change the region of equivalence in a running test. It's not a good strategy because it will change the maximum sample size of the test. It will change the entire meaning of what you mean by equivalent. So decide it in advance. And actually, I'll cover the sixth part as well. Sixth tip, that you should ideally have an equivalence region individually defined for every metric that you are dealing with. And you should not change it in every test as well. Ideally, a metric should define what is equivalent for that metric that you have. Finally, the last tip is that you should decide before running the test whether it's a superiority test or non-inferiority test, and you should not keep switching in between. So that's not a good strategy. So this is precisely all I had for this webinar today. We are closing almost 15 minutes early. If there are any questions, any discussions, I am very much willing to even invite any one of you on the webinar screen, and we can have some questions one-to-one.